Hello everyone, my name is Triu, and this is a joint work with Yuhai Wu, Kwok Le, He, and Tang Leung on a recent paper named Solving Olympiad Geometry Without Human Demonstrations. Let me first explain a little bit about the context of our work. Olympiad here in the title stand for the International Mathematical Olympiad, also known as the IMO, the oldest and the most prestigious math competition in the world. The IMO is also at the same time a grand challenge for AI research because at the moment computer capability is still far below human level. And so we look at this competition and we ask the question, what would it take to deliver a breakthrough here? And as it turns out, for the narrow domain of geometry, we actually have a chance to significantly narrow down the gap between machines and top human performances. Coming up next, let me walk you through three of my favorite examples of the type of problem and solutions that tend to appear at these mathematic competitions. And then together, we'll make some observations about them. That is, what are the hard things about solving these problems and what are the easy things about solving these problems? And then based on these observations, we will together propose a solution for them. So first example, this is a question in number theory where we ask, how many primes are there? So we know that there are an infinite number of primes, but the proof would start out by assuming that there's only a finite number of primes from P1 to Pn. And then once we have this, Euclid, a mathematician living many thousand years ago, would suggest that we should build a new number P as a product of all these prime numbers and then add 1 to the product. And thanks to this construction, this new number is not going to be divisible by any of the primes, and it is also larger than all of the primes. And so it have to be a new prime that is missing from the original list of all prime. Therefore, we have a contradiction, and therefore we have to have an infinite number of primes. Let me point you to the blue proof step where Euclid constructed a new number out of thin air. This construction is the genius part of the proof because Euclid have managed to do something mathematicians nowadays call pulling a rabbit out of the hat, which is why I'm placing a rabbit icon over here. The remaining part of the proof is relatively more mechanical. So with this first example, I'd like to introduce you to the first important concept in our work, which is the rabbit. Moving on to the second example. This time, let's say we want to solve an equation. 4 to the x plus 9 to the x plus 1 equal to 6 to the x plus 1. So this is a very, very intimidating looking equation to me because I only have very standard high school training and I only know how to solve quadratic equation where there's a formula to follow. However, back in high school, I also have a very clever friend who would come along and look at this problem for a few seconds and suggest something like this. How about we construct A as 2 to the x and B as 3 to the x plus 1 and see what happens. So what happened is that the original intimidating looking equation would become something that I'm very familiar with, which is exactly a quadratic equation. So at this point, I can just follow the formula that I'm familiar with to derive all the way until the solution. In fact, one can imagine that there's multiple different mathematical software that can easily automate away this part. For example, Wolfram Alpha would not have any problem finish the proof as long as you give it the two rabbits A and B. So with this example, I'd like to introduce you to the second important concept in our work, which is the symbolic engine. The symbolic engine role here is to implement very efficiently common knowledges, common formulas, and procedures in problem solving. With that, let us come to the last example. This time we look at the narrow focus of our work, which is geometry. So in geometry, we are usually asked to first construct a bunch of points and lines. In particular, for this problem that we're looking at, which is the IMO 2018 problem 1, we are asked to construct points A, B, C, and then D, E, and then F, G, according to some formula that I'm not showing here. Then once we finish constructing this diagram, we then are asked to prove something that happened. And in this problem, we're asked to prove that these two red lines are parallel. For me, I have no idea where to even begin with solving this problem, and I'm not even qualified to be at the IMO. But let me, again, borrow my clever friend who would come along, look at this problem for a few seconds or a few minutes, and suggest something like this. How about we construct the point M as the midpoint of arc AB and the point N as the midpoint of arc AC and connect them and see what happens. Well, this time I'm not seeing anything happen because this did not become a quadratic equation that I can follow as an easy formula to solve. However, there is an existing symbolic engine that can finish the proof within just a few seconds up to a few minutes as long as you give it the two rabbits M and N. In geometry, we also call the rabbits magic construction or auxiliary points and lines. In the paper, we also introduce two other examples in graph theory where we try to tile a plane or proving an inequality problem at the IMO. Both of these examples also exhibit the structure of rabbit and the symbolic engine, but I won't be going into details here because after these three examples, I think we all got the point. The point here is, or the general observation here is that given a hard problem, we usually have to come up with one or more rabbits in order to transform the problem into a more mechanical state in such a way that the symbolic engine or the mechanical solver can just take the problem and then solve it. But if the solver failed to solve the problem, then we can always come back and ask for more rabbits. And then we keep doing this in a loop until we find the solution. And so with this observation, our solver here pretty much reflect the structure of this observation, where we build a neural language model that is trained to propose magic construction, and then we build a symbolic engine that is tasked with handling all the mechanical cases and the mechanical deduction in geometry, and then we put these two components into a loop so that we obtain a neural symbolic solver named AlphaGeometry. Before moving on, let me point to an important fact, that is, the observation of neurosymbolic structure is not a novel observation that is made in our work. In fact, in 2020, Polu and Suskeva, in their first work that have introduced language model to the problem of theorem proving, have already pointed out that a major limitation of theorem proving compared to human is, in fact, the ability to generate original mathematical terms, meaning generate the rabbit, and this limitation might be addressable via the generation from language models. And this is exactly the structure that we are following. The difference here is that previous work have been training language model on human demonstrations, where the domains of mathematics that they are solving have a lot of data to train on. However, in our case, for geometry, we do not have much data to train on, and so we have to figure out the problem of generating synthetic data to train the language model on. For the remaining part of the talk, first, let me explain very clearly what is the input and output to our solver, and then we would go into the detail of the two main components of the solver, which is how do we even build a symbolic engine for geometry, and how do we even train the language model to come up with all the rabbits. And then we would go quickly through the results, and that would be the end of the talk. So let's talk about the input and output of our solver. Given a geometry problem that is stated in natural language, there have to be me who step in and manually translate this problem into a geometry-specific representation in such a way that a computer can automatically parse and process it. Then we feed this representation into AlphaGeometry, which will run this neurosymbolic loop that hopefully in the end return a solution that is also represented in this domain-specific language that we can automatically parse and verify. However, because the grammar of this language is very natural to read, we also have the option to manually evaluate these solutions, just like how human solutions are evaluated at the IMO. Namely, we submitted some of AlphaGeometry solutions in the year 2000 and 2015 to Evan Chen, who is the coach for the Olympiad team of the US. And we are recommended to receive a full score for these 2 years, meaning passing the bronze medal threshold. Moving on, in this slide and the next slide, I'll talk about the symbolic engine, which is the first important component of our work. The symbolic engine that we built in this work is named DDAR, standing for Deductive Reasoning and Algebraic Reasoning. The goal of this symbolic engine is to take in a problem and then attempt to solve that problem by following mechanical rules and common knowledges in geometry. And I included a fraction of these rules in geometry in this box. Here, just to read one out loud, at line 7, what we're having is the rule that's saying that if E is the midpoint of AB and F is the midpoint of AC, then EF should be parallel to BC. So the problem of curating this list of rules and efficiently following them has already been solved by many work in the past. Our contribution here in building this symbolic engine is to recognize that in order to solve a lot of these advanced high school problems, it is also necessary to be able to manipulate algebraically geometric quantities like angles or ratio segments or distances between points. And our contribution is to recognize that all of these algebraic manipulation is similar to a process called Gaussian elimination. We explain this in detail in the paper, but for this talk, I'll skip it and keep it high level. Overall, the symbolic engine DDAR have these two components that combine both deductive and algebraic reasoning. which itself is a very powerful symbolic engine in order to solve a lot of geometry problems. In particular, when tested on a test set of 30 Olympiad level geometry problems that is taken from the IMO between 2000 and 2022, DDAR is able to solve 14 problems, outperforming the previous state-of-the-art at 10 problems. There is a footnote here for the state-of-the-art method. That is, this method have a theoretical guarantee to be able to solve all 30 problems. However, the time complexity and memory complexity of these algebraic methods is really large. That's why we have to limit it within the IMO time limit for each of the problem, which is 4.5 hours. We also let this method run for 10 times longer the IMO time limit, which is around 48 hours. This method can still only solve 10 problems. So 14 is already pretty good, but it's still very, very far away from 26, which is the performance of the average human gold medalist. And the reason why we have this such a big gap is because no matter how strong we build this symbolic engine, there's still a very important key missing ingredient that humans are brilliant at doing, but not so brilliant at explaining how to do it, which is coming up with the rabbit. So at this point, we said, let's bring in the power of learning from data. And we train a language model to come up with this rabbit in such a way that it can also work with the symbolic engine DDAR and bring the final result to 25, which is somewhere between the silver and gold medalists. An important note here is that this evaluation is only on geometry, but the IMO also include 3 other domains of mathematics, including number theory, combinatorics, and algebra. So for the remaining part of the talk, I'll just explain exactly how do we even train a language model to generate these rabbits. And the first question that we ask whenever we talk about training a language model is how do we even get the data to do so? And as I mentioned earlier, in geometry, we don't have data to train language model on. And so we have to figure out a way to generate these data synthetically. And so for the slide, I'll walk you through a very simple 3-step recipe in order to generate synthetic theorems and proof. In the first step, we would do something called sample, where we randomly sample a bunch of mathematical facts like A equal B and B equals C. And then in the second step, starting from these initial facts, we would try to deduce new facts. For example, in this case, we can deduce that A equals C thanks to the transitivity of equality. After the second step, what we're having is a tree where we have one single root and 2 leaves. In the third step, we would serialize this tree into a string so that we can train the language model on. Namely, we would serialize this tree as follows. First, we say theorem, and then we list all the leaves, meaning let A equal B and B equal C. And then we say that we want to prove the root, A equals C. The proof here would just describe exactly how we connect the leaf to the root. In our case, this connection is very simple. We have a single proof step applying the transitivity of equality on the 2 leaf A equal B and B equal C. So far, we haven't seen any rabbit being generated yet. And let me point out that in the literature, there has already been a lot of work that follow very similar recipe to generate synthetic data. And to point one out, a work in 2021, where the author managed to train a theorem prover using purely synthetic data. And to quote their paper, there is a limitation of this recipe. That is, there is a class of theorems that it cannot generate. That is the theorems that introduce new symbols, new axioms, and new hypotheses, which is exactly the rabbit. And here come the core contribution of our work. That is, we come up with a new twist to this recipe that will be able to generate these rabbit in order to train the language model. And in order to explain that, let us go through this same recipe again the second time, but this time let us look at a slightly larger example, where in the first step, we generate 3 random facts. AB equal AC, DB equal DC, and DBC is on the same line. These 3 leaves can be represented in a diagram on the right here, where we have a triangle ABC with 2 equal sides and D as the midpoint of BC. So that's the first step. In the second step, we would try to deduce new facts from these 3 leaves, and we ended up at the root of the tree, the conclusion that angle ABC is equal to angle BCA, which is represented by the 2 gray angles at the base here. That's the second step. In the third step, we would serialize the tree into a string of theorem and proof, where we say theorem, and then we list all the leaves, which is to say there's a triangle with 2 equal sides and a midpoint, and we want to prove the root. That is, the 2 angles at the base are equal. And the proof here would have two steps, where the first step we would derive this intermediate sub-goals before using that sub-goal in the second step to derive the final conclusion. So far, what we're seeing is still exactly the same recipe, but there's something special going on here. And the special thing is D being the midpoint of BC, highlighted in blue. There are two things that is special about this. First of all, D being the midpoint of BC is not necessary to state the theorem, because any triangle with two equal sides should have two equal angles. Doesn't matter whether that triangle have a midpoint or not. However, D being the midpoint of BC is necessary for the proof to work, because D being the midpoint of BC correspond to the second and the third leaf, which are necessary to connect the first leaf to the final conclusion. And so with these two observations, we perform the following transformation of the string, where we bring D being the midpoint of BC from the theorem statement to the proof, and ended up with a new theorem. That is, given any triangle with two equal sides, we want to prove that there are two equal angles. And the proof would start out with constructing D at the midpoint of BC. So the only question left to ask in this slide is, given these three random leaves, how do we even identify which part of these leaves would constitute the rabbit part? And to answer that question, we also have a four-step recipe. In the first step, given a random set of leaves, what we'll do, of course, is we're going to have to build a tree. And in the second step, we look at the conclusion and we do something called conclusion traceback, where we go back in the opposite direction of these blue arrows to identify the set of leaves that are necessary to make the conclusion. So in our case, this set of leaves consists of all these three leaves. And in the third step, we also look at the conclusion, but this time we only look at the object within the conclusion. Namely, in this conclusion, the objects are the point ABC and the two angles ABC and BCA. And then we ask the question, based on which leaf are those objects constructed? And as it turns out, these objects are only constructed based on this single leaf, AB equal AC. And in the last step of the recipe, we simply check the difference between these two sets, which would give us the rabbit that we're looking for. Before moving on, let me point out that this recipe seems to be pretty general, because all that we're doing is building a deduction tree and then do a bunch of tracebacks along its edges. However, we don't want to give the false impression that this can be easily translated to any other domain. For example, to make this recipe to work on geometry, we have to employ a lot of specialized solutions. For example, before any of these steps in the recipe happen, we need to make sure that we have a domain-specific language and then curate a list of deduction rules. And then in order to build the tree very efficiently, we need to make use of the symbolic engine that is built only for geometry. And because we're building the tree using specialized solution for geometry, tracing back along the edges of this tree also require specialized solutions. For example, in our paper, we pointed out that in order to trace back along this tree, we need to perform a bunch of algorithms like minimum spanning tree or solving some linear programming problems. And then in order to do object traceback, we need to represent geometry in both constructive logic and classical logic and be able to translate between them. So overall, this recipe seems to be general, but to instantiate the recipe for any domains of mathematics, there are a lot of engineering and technical challenges that are needed to be solved. With that said, we have all the recipe that we need. The only thing left is to scale up and generate as much synthetic data as possible. Here is a sample of a visualization of 12 random sets of leaves. So each of these diagram is representing one random set of leaves. And we'll build a tree for each of the diagram, and then we do the traceback, and then we will extract a lot of synthetic data from them. In terms of number, for each of the diagram, we sample up to 60 leaves, and then we run these processes in parallel over more than 100,000 CPU workers over many days. And in the end, we examine around 500 million unique theorem and proof strings. And as you can imagine, a lot of these strings are actually isomorphic to each other, because the same tree can be serialized in many different ways. And we try to account for that too. And at the end, after deduplication, we get around 100 million pairs of theorem and proof. So what do they look like? This is what they look like. Here, what you're looking at is a histogram of tree sizes, meaning proof length. And as you can see in this histogram, most of the synthetic proof that we generated is concentrated mostly on the left, meaning a lot of proof here is really short. In fact, more than 99% of them is actually shorter than the average proof length for the IMO problems, which is around 50 proof steps. However, we also have a good spread of synthetic data all the way out here, with the longest proof being 247 proof steps. And just to take some for examples, in the bottom left here, what you're looking at is a trivial theorem that we have discovered using this synthetic data generation, and it looks very trivial. What this theorem is saying is that if you have these 4 points with 2 right angle, then they should be on the same cycle. And the proof of this is simply a single step applying the corresponding deduction rule. But then for the proofs that are between 20 and 30 proof step long, we have a bunch of very well-known theorems that we have discovered from scratch using this synthetic data generation procedure. And all the way out here is the longest proof that we found in our synthetic data set. This proof step is asking us to prove that these two blue angles are equal. And in order to prove this, we need to come up with 2 rabbits and then follow that up with 247 deduction steps. So overall, out of these 100 million training example, around 9% of them, which is around 9 million theorem and proof, would involve some rabbit. The remaining 91% can be solved with pure mechanical deduction, meaning they can be solved just by applying DDAR. What we did with the training is first we pre-trained a language model from scratch on all of the data before fine-tuning it on the smaller size slice of data that involved the rabbit. And once we finished training this language model, we put it in the neural symbolic loop with the symbolic solver DDAR, and then test it on the test sets and see how well it performed. So you already know the final result. AlphaGeometry is performing somewhere between a silver and a gold medalist on a test set of 30 Olympiad level geometry problems. And we also tested AlphaGeometry and compared it with previous baselines on a larger test set consisting of more than 200 geometry problems ranging from trivial to very hard problems. And AlphaGeometry is still coming out on top, solving almost all of the problem. However, the gap between AlphaGeometry and other baseline aren't that large anymore. So in the paper, we also provided a lot more quantitative and qualitative analysis, as well as all the technical details that I have skipped over in this presentation and only mentioned by name. So please refer to the paper if you want to fill in these gaps. And with that, thank you for listening.